Hello boys, how are you? Hopefully you're okay, you're not stressed up or anything. So this is my first attempt, sorry if it's not perfect. So let's start off with, actually this week we should be starting with this new chapter. So I start off with the first topic, topic 4.1, which is variety of minerals. Okay, variety of minerals. So under this topic, actually there are three objectives. Right, so first off, this one I took from the textbook. It's the definition of mineralogy. Right, it's the study of minerals. And then these are minerals in the form of ores, which you usually call simply as stones. But they're actually ores, minerals that you usually find in Earth's crust. So they come in different colors, texture, and striation, as you can see. Right, what are the names of these ores? Let's listen to this a bit.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to answer the question, what is a mineral? Mineralogists define a mineral as a substance that is natural, which means that humans don't manufacture it, is a solid, that is, it keeps its form at room temperature, and has a distinct chemical makeup, which means it has a specific chemical formula that's consistent throughout the mineral. This is true whether the mineral is made of a single element or of a combination of elements. A specific chemical makeup distinguishes minerals from rocks, which are mixtures of many different materials. In addition to these qualities, most mineralogists agree that minerals are abiogenic, that is, not produced in living organisms, and that they have atoms that are arranged in a specific order. This property results in many minerals taking the form of crystals. Mineralogists have identified almost 5,000 unique kinds of minerals. They're classified by physical properties such as color, hardness, luster, how they reflect light, and radioactivity. Despite Earth's wide variety of minerals, about 90% of our planet's crust is made up of minerals composed largely of silicone and oxygen, called silicate minerals. The most common silicate minerals are called feldspar and quartz. Minerals don't just make up the Earth, they also make up about 4% of your body mass. Because minerals can't be made by the body, it's important that we get them in our diet. Some of the more important ones include calcium and phosphorus, important for bones and teeth, iron, essential in red blood cells, and potassium and sodium, required for healthy nerve cells. We also require trace minerals like copper, zinc, and iodine. Humans use minerals in everything from cereals to batteries to shampoos to pet foods. In fact, at least 30 minerals are present in the computer you're using to watch this video.
For thousands of pounds.
Okay, now let's continue. So the various forms of minerals in Earth's crust, they come in the form of elements and compounds. Okay, solids mostly. Remember, mercury is also a mineral in the form of element, but it is in liquid form. So they are found naturally and has definite crystalline structures and chemical compositions, which we will look into later. So minerals as a whole is divided into these two major groups, elements and compounds. Now please recall the lesson on what element and compound means. It's from what you studied in Form 1. You need to be clear on this, otherwise it will be quite difficult for you, because there are a lot of chemicals involved in this, especially in the naming of the compounds. Okay, next we start with natural elements. Usually they are non-reactive minerals, which means they do not react chemically with other elements, and they are chemically stable. So the most famous example would be gold, diamond, and silver. So you can imagine what they are usually used for, jewelries, right? And you don't usually see your the gold jewelries getting rusty or anything because of this feature, this characteristic. Then second off, we have natural compounds found naturally. Right, these are reactive elements, chemically with other elements to become chemically stable. So they need something else to combine with them in order to achieve stability, and that forms compounds. Okay, so they come in the form of compounds. Okay, on its own they are not stable, so they have to find a friend. Right, so reactive metals with another non-metal will form a chemically stable compound like this. So these are the common names. Okay, we will look into detail later what their chemical contents or chemical compositions actually are. So we have bauxite, hematite, galena, and cassiterite, just to name a few. Then we have, alright, how they are formed. Natural compounds are actually metal element combining with a non-metal element to form the compound. Okay, for example, metal. Okay, by now I think you know examples of metals. The common ones would include things like iron, lead, calcium, potassium, just to name a few. So any metal that combines with oxygen forms a metal oxide, which is a compound. Another form of natural compound is metal carbonate, which consists of metals combining with a non-metal, with two non-metals in fact, oxygen and carbon, to form a metal carbonate. You see here the names, the metal, how to name them, the metal don't change. It's what the non-compounds that they combine with that will determine their end name. Okay, and then another one is metal with sulfur. Metal with another non-metal, sulfur, forms a metal sulfide. Okay, if it combines with sulfur, it ends with the name, the new name, sulfide. And another one is a metal with a silicon and oxygen, forms metal silicate. So please take note of how they are named. Right, metals combining with these non-metals forms these natural compounds. These are the chemical names. So just now you saw cassiterite, galena, and all these. Those are the common names. These are the chemical names, which clearly indicates the chemical compositions of these natural compounds. Right? Again, I repeat, the metal part you don't really change much. It's the non-metals that they combine with that will determine the end name. These are the end names that I meant just now. So they are either an oxide, they may be a carbonate, they may be sulfide, or they may be a silicate, depending on the non-metals they combine with. Alright, this is what you learn, I think, in Form 1, the periodic table. Right, as you can see here, these are metals, but we don't usually cover much. We don't usually touch on this a lot. Maybe a bit of this, zinc, copper. Usually we use this, not this, this one, the second group, magnesium, calcium, and then these are the non-metals, the one in green, and these are metalloids, which includes silicon. So silicon metalloid means it shows non-metal feature at times and metal features at other times. So that's what it means by metalloid. Right, this one you can find in your textbook. So this is how you name them. Okay, this is the common name. So let's say hematite. Hematite is actually ferrum 3 oxide. What does this name means? It's actually a combination of iron, which is a metal, with oxygen, a non-metal. So iron plus oxygen, it's actually iron oxide, or sometimes known as ferrum oxide. Okay, and then we have cassiterite. Chemical name, cassiterite. Scientific name, stannum oxide. It's actually a combination of metal, tin, with non-metal, oxygen. Quartz is silicon dioxide. It's silicon plus oxygen. Bauxite is actually aluminum oxide. Combination of aluminium plus oxygen. Then you have galena, plumbum with sulfur. And then pyrite, it's actually iron pyrite. Ferrum with ferrum sulfide, means iron plus sulfur. Then calcite, it's actually calcium carbonate, means it's a combination of calcium plus two non-metals, carbon and oxygen, just to give, just to name a few. So I repeat, metal with the non-metal oxygen gives you an oxide. Metal with two non-metals, non-metal elements, carbon and oxygen, will give you a carbonate. Okay, regardless of who the metal they combine with, it's the two non-metals, it's the non-metals that makes the decision on what their end name would be. And then metal with silicon and oxygen will give you silicate, and then metal with sulfur will give you a lead sulfide, sulfide, metal sulfide. Okay, the compound sulfide. So characteristics, they are mostly hard. Okay, take note of the word most. And then they mostly do not dissolve in water. But upon heating, some of them do show some kind of response. Right? This means heating. I use this symbol to represent heating. So let's say metal oxides. If you try to heat metal oxides, you will not see any change because it's already in oxide form. Do note that oxide is the most stable. There's nothing you can do to it. It's already the final form. It can actually, possibly exist in the natural environment. Oxide is the last one. If it is a carbonate, it can actually degrade, or it becomes a metal oxide by releasing carbon dioxide gas. And then if it's a sulfide, it also reacts by becoming an oxide itself, because heating involves reaction with oxygen, so they become metal oxide and releases the gas sulfur dioxide. So these are gases. Okay, these are the gases. So some examples that you can take note of: calcium carbonate, that's the natural compound in the form of, it's a metal carbonate. When you heat it, it will become an oxide and releases carbon dioxide gas. If it's a sulfide, it will become an oxide and releases sulfur dioxide. How about aluminium silicate? What do you think? Alright, that one I leave it to you. And then these are the uses. You find minerals in all sorts of things that you use daily, whether you realize it or not. Some you even consume in your diet. Alright? So important minerals and their uses. This is the last part for the topic. Aluminium is, I think you know how it is widely used for bodies of cars, aircrafts, motor vehicles, as well as the canned drinks. And then packaging, all sorts of packaging, food packaging especially. Chromium is, as you can see there, chromium plates, dyes and paints and steel alloys, cutleries. So those cutleries that actually rust after some time means they are not actually pure stainless steel. It is plated and you call it chromium. Then we have cobalt, usually blue in color. So it's usually used for pigmentations. It's pigments for dyes, colors, to give colors. Gold as jewelries, also used in dentistry, as well as what you find in your cell phone, although not much. Okay, and then we have steel, which is a combination of alloy of iron for buildings and machineries. This one is magnesium, to name one of it, for firecrackers, flares. And then mercury is used here in this bulb, as well as batteries and thermometers. The thermometer, the most common example that you have actually seen with your own eyes. And then molybdenum for aircrafts and industrial motors, just to name some of the minerals. And then if you look into detail, asbestos, it has a high melting point, means it is heat resistant, so it doesn't conduct heat, so it is good to be used as firefighter suits. Also for racers, F1 drivers, they wear this special suit made out of this asbestos. Right? It is heat resistant, and usually if you have this kind of roofing, especially in old houses, we don't usually see this a lot nowadays. This kind of roofing is actually, if you go inside, it's very cooling because it repels, although it doesn't conduct heat. Alright, Second one is iron oxide, naturally red in color as dyes. Okay, pigments in paints used in cosmetics. And then we have silicon dioxide. Okay, silicon dioxide, the most common source you find in the natural environment is what you usually call as sand. Okay, I think most of you know that glasses, the main source is sand, silica, right? So it has high melting point, it is heat resistant and chemical resistant. So this is why glasses are used to store chemicals. They don't react with the chemicals they store, unlike plastic. Okay, and this is the chemical formula: Si for silicon, O2 for 2 atoms of oxygen that it combines with to form the compound silicon dioxide. And then we have aluminium oxide. It has high hardness, usually used or found in sandpapers for woodwork. Okay, if you still do this in RBT. And then silicates, also same family as silicon, silica, all know this. It has electrical resistance between conductors and insulation, so you usually find them in electronic chips, right? And then magnesium carbonate. Magnesium carbonate, usually carbonates are never mind. It has low solubility in water. Hygroscopic means it absorbs moisture. Okay, if you like to watch sports, I think this is the one, the powder they use for those involved in weightlifting. Okay, they powder their hand before they go on stage and lift the weight. Right, this is what they use, this is powder. Right, and then kaolin, the common name. Aluminium silicate, the chemical name is hard and chemical resistant, suitable to be used in dentistry for dental crowning. Okay, and then calcium compound. Right, calcium compound is actually very interesting because there are so many experiments that we can do to it. So these are the common examples: limestone. Okay, you find this to make roads. Before they actually tar the road, they put this as the base. The marble, tabletops, floors, chalk, and calcite. Right, turn to this.